Hello everyone, myself Harish Anil Jumkandi from MS Institute of Technology, the presenting author for Road Characterization for Digital Maps. Co-authors are Aman Vora and Chaitanya, and we are mentored by Mrs. Lakshmi S. The sole motivation for our project is the accidents. There are a number of problems which cause these accidents. Number one, the poorly maintained road conditions. Number two is unwarranted weather changes. There were certain attempts which are presently acting as an intelligent systems which in a high-end vehicles. This itself motivates to have the same systems in the lower-end vehicles too. Moreover, these systems are not efficiently tackling the problems of road accidents. To act upon this cause, we present our project which has the benefits. We mainly concentrate on urban and rural masses. This is due to we are updating the whole map with respect to the local and non-local coordinates iteratively. It also has a civic importance as it provides a method for the governing body to maintain the record about the road inconsistencies. In the course of this project, we had to reference certain literature. The best known methods were these three. The most novel method was to use the mobile units which were embedded with accelerometers. The second best method was to use vision systems like cameras in specific open slam technology to create the map of coordinates. And to act upon the cause, the study of gyro-free tree analysis was also useful. With this, we propose our 12 features. We hereby give a more generic solution and a more cost-effective solution. It also has a self-learning and iterative feedback system. When a system is learning, there is a less chances of errors. It also has less efforts in calibration with respect to every other automobile. Hence, it has a benefit.
For the proposed onboard system, we have various features as shown. First, we need to record the inconsistency. For that, we are using the ADXL 335 accelerometer. Next, we also need to know the positional coordinate of the vehicle. For that, we are using the SkyTrack GPS module. These two data are then framed together, then they are sent as a single database through the wireless Zigbee RF module to the offboard system, which is the BeagleBone Black. That was the transmission part. And now in the reception part, the vehicle receives the data about the forthcoming inconsistency. The data is interpreted by the control unit, which is an MSP 430 G2553 controller. This device reads the data and it interprets about the inconsistency character and it warns the vehicle about the inconsistency for the next few vehicles coming along. Here is how we exactly record the inconsistency. We are using a GPS module and an accelerometer module. In GPS module, we receive several NMEA characters and we are narrowing down to the GP-RMC string, which is the most important one for us. We also first need to know whether the data is a valid data or invalid data, which is noted by the status of the GP-RMC string. And yes, we also record the latitude and longitude of the string. And for the inconsistency, which is recorded by the accelerometer, we have classified the inconsistency into various types. For example, we have a hump, which is represented by H, pit by P, elevation by E, tilt by L or R, and no inconsistency we have to transmit an N. For example, here is how our frame is, how our database is stored. As you can see, I have used the GP-RMC data and it transmits till the east location, which is the longitude, and then in blue is my inconsistency. So this was an example of the framed data. For the offboard database storage, we are using a BeagleBone Black. It receives the framed database string which is sent from the vehicle. It also stores new inconsistency information, and the BeagleBone Black also calculates the distance between the vehicle and also the nearest inconsistency. If this is between a safe limit, then it transmits the warning character to the vehicle. Why a BeagleBone Black? The BeagleBone Black has a massive memory capacity for a standalone unit,
implementation of the project mainly consists of a decoder circuit, an MSP430 controller, and an L293D driver circuit, a GPS module, and a ZigBee module. The entire vehicle is powered with a 12 volts power supply, but the decoder and the MSP430 circuits work only with the 5 volts and the 3.3 volts respectively. Hence, the 12 volt supply is converted into 5 volts using LM7805, and the 5 volts is again stepped down to 3.3 volts using LM3940. Both the GPS module and the ZigBee module support only UART. Hence, we interface the GPS module with a hardware UART and the ZigBee module with a software UART. For the locomotion of the vehicle, we are using L293D driver circuit and 4 motors. But in the L293D driver circuit, we have only two channels. Hence, we are connecting 2 motors in parallel to each channel. Coming to the problems faced while designing the prototype, the inaccuracy of the GPS has been compensated with a large distance, and the ZigBee module range could not be communicated wirelessly with a large distance. And we are using 4 motors, hence there is a need of high current battery to drive the motors.
At the end of the hardware implementation, this is how design prototype looks. To go to the software implementation of our project, we have 2 different flows. This is for the onboard system and that's for offboard system. The basic steps in this flow is, first, we need to acquire the vibration data and the GPS coordinates data that is done by the sensors. Then these data is subjected to validation, that is the character A and V of the GPS string. Then these characters are annotated and classified as humps and bits. Then the same thing is framed into a single string to create a database string, which is transmitted to the offboard system, and there it is further processed. At the offboard system, we have a process where the coordinates are stored and the inconsistencies are stored. Based on the coordinates of the received data, a warning is sent to the onboard system, and based on the warning character, the required action is taken by the committer. So that's how the software implementation is.
Coming to the results of our project, the vehicle was subjected to testing in the local campus. The live inconsistency results were observed, and then these were stored as a database and transmitted to the offboard system. There were several limitations to the project. First, the prototype and the inconsistencies had to be in the same scale. Next, there was an inaccuracy in the GPS module and a very limited range of the ZigBee module. So here we have 3 diagrams. This was the recording of the bit, and here we received the database. Here is the bit character, and then at there the vehicle was passed again to the same location, and the P LED was lit, and that was the warning system.
Coming to the conclusions of our project, at the end of the project, we had certain things accomplished. Number 1, the vehicle prototype, which was designed, was able to map the road inconsistencies, its coordinates, and was able to communicate with the offboard system. Number 2 was the vehicle system was warned about the forthcoming inconsistencies, and their database which was getting generated was iteratively updated about the forthcoming inconsistencies and the new inconsistencies of different roadways. Coming to the future, this project has had a time hindrance and it can be implemented at a higher level. Hence, we provide a chance of future. The project can involve a web cloud interface. As we have used BeagleBone Black, which has a hosting service, we can use the web cloud interface to eliminate the limited range of wireless devices. Secondly, the direction of the automobile in a particular lane can be more specifically addressed and more specifically warned about the inconsistency with respect to that lane. And lastly, the automobile in which the system has been incorporated can be made more intelligent. By this, the whole system and the commuters can have a comfortable journey. Coming to the references, we had 3 major references. First reference was how the smartphones or the mobile units with the embedded accelerometer was incorporated. Secondly, how the open slam systems or stereo vision systems were used to design an unmanned ground vehicle which in a multi-terrain was subjected to testing. Thirdly, we had a very cost study where gyro-free inertial navigational technology was explained. So these were some of the references which we had referred. Coming to the acknowledgements, we thank our parent institute, MS Ramaya Institute of Technology, for extending all its support and facilities to us. We thank our principal, Dr. S.Y. Kulkarni, for his continuous support. We also thank our head of the department, Dr. Setu Selvi, for extending the moral support and all the facilities throughout the project. We thank our mentor, Mrs. Lakshmi S., for helping us in all the technical difficulties and also staying there for us. We thank our seniors, Mr. K and Anil K, for helping us throughout the project. We thank Ankit Raj, Sankha, Abhishek Raj and Marav Patnaik for helping us in video making and the related softwares. We also thank Texas Instruments for giving us wonderful technology. Thank you.